The previous topic was about Fermi-Dirac statistics, and then we found a distribution function which gives you the appropriation number of particles in any particular level. So part of our job was to find a relevant formula to our systems according to statistics. And we named it Fermi-Dirac statistics. Then we applied the principles of physics, of our mechanics, of our systems. We applied that statistics to our system. And we found the distribution function for our particles, or spin-half particles, right? Which was the number of particles in any level I is equal to Gi divided by the exponential function of alpha plus beta Ei plus 1. That was the distribution function, right? Now we want to further understand a little bit the Fermi-Dirac statistics, to understand it a little bit, and to understand what is the thermodynamic probability of a system of a small number of particles which will obey the Fermi-Dirac statistics, the Fermi-Dirac principles, like the Pauli exclusion principle, and we will find the total number of microstates, how many macrostates are possible, right? And what is the most probable distribution. So let us start with an example. Page number 319. Sears and Salinger. Suppose, is it visible to you? Is it clearly visible? I hope. Okay. So suppose we have 6 particles which obey. Suppose we have 6 particles. Number of particles is equal to 6. And they obey Fermi-Dirac statistics. Suppose we have particles. Suppose we have a system of equally spaced energy levels. Equally spaced energy levels. Suppose our system is such that all the energy levels are equally spaced, such that the separation between any two neighboring levels is small e. Right? Separation between the level is equal to small e. They are equally spaced, and the separation between them is small e. These are the conditions of our example. And the total energy of the system is equal to 6E. If E is the energy of between the two layers, then the total energy of the system is 6E. And further, uh, lit. Each energy level is 3 times degenerate. There are 3 states in each energy level. That is G, right, I is equal to 3. We have 3 states in each energy level. This is our system, right? This is our system. These particles obey the Pauli exclusion principle. So they obey Fermi-Dirac statistics. Okay, so this is our systems. This is our system. We have to find the thermodynamic probability of each state. Thermodynamic probability of each macro state. The thermodynamic probability of each macro state. And the total number of microstates, how many microstates are there in the system? The total number of microstates, the average occupation number, average occupation number of each level. हर एक लेवल इसकी एवरेज ऑक्यूपेशन नंबर क्या है? On the average, how many particles are there in each energy level, not state? We are talking about energy level. How much is the number of particles, average number of particles per energy level? We can also find the most probable distribution, right? The most probable distribution. We can also find the most probable distribution. So let us draw our system, right? Suppose our system is like this. There are energy levels. These are energy levels, equally spaced energy levels, suppose we have, right? It starts from 0, that is the system. Starts from 0. That is E. That will be 2E. That will be 3E. 4E. 5E. 6E. And so on. Right? So let us, and further it says, the example says that there are 3 states in each energy level. This is energy level number 1, that is 2, that is 3, that is 4, that is 5, that is 6, that is 7. I is, that is what? I is equal to 1, I is equal to 2, 3, 4, 5, 6, whatever. These are the energy levels. And we are said that each level has three states. So there are तीन बर्तन हैं हर एक उसमें, हर एक एनर्जी लेवल में तीन स्लॉट्स हैं, तीन कुर्सियां. They have three energy levels. So the first distribution could be like so. Now this is our system. We have to place our particles in this system so that the particles obey the Fermi-Dirac statistics, which is one particle in one state. The particles obey the Pauli exclusion principle, one particle per state. So if we start from the bottom, हम कहते हैं ना, लोग सबसे पहले जमीन वाले ग्राउंड पे जो है वो कमरे ऑक्युपाई करना चाहते हैं, इसके बाद वो ऊपर जाते हैं. So the particle, suppose they would like to stay here. So how many particles can be accommodated at the most here? They would be like three, right? Three particles, तीन पार्टिकल ने इस लेवल को ऑक्युपाई किया. Now this level is full. No more particles can come here. According to Fermi-Dirac statistic, we are doing Fermi particles. We are playing with Fermi particles. So no more than three particles can be placed here because that will violate the Fermi-Dirac statistics. That will not be in the nature of the particles that we are dealing with. We are dealing with the nature of the particles in which they obey the Pauli exclusion principle. And the Pauli exclusion principle means that only one particle per state. So there are only three particles here. So the three particles that are left, because we have total 6 particles. So the 3 particles, they will then come to the next state, right? So suppose one comes here and one comes here. Right? Okay, look. Here, if we put all the 3 particles in this level, if we put all the particles, all these 3 particles in this level, level number 2, which has energy E, then the energy of the system will be 1E plus this 1E plus this 1E. The total energy will become 3E. The total energy will then become 3E, which is not according to the condition of our question. The example says that the total energy should be equal to 6E. 6E should be the total energy. Therefore, 2 particles have come here. It should go somewhere and not here, so that the condition of the total energy is also fulfilled. So, look, where should it go now? Where should it go now? 2E is here. So, 6E, 6 minus 2 is equal to 4. So, the remaining particle must go to here, where the energy is 4E, where the energy should be 4E. So, that particle, suppose, is here. Now we have the condition fulfilled, right? We have the condition fulfilled. 3 particles here. No more particles can come to this level. Now, two particles are here in the next level, which aid together and gives you energy equal to 2E. Now, the next electron is going to the level which is 4E, has energy 4E, so that the total energy is equal to 6E. Right? Therefore, it goes here. This is now our electrons are distributed in all the energy levels and in accordance with the conditions of the example. In accordance with the conditions of the example. So this is macro state number 1. Macro state number 1. इन पार्टिकल्स का जो मैक्रो स्टेट बन सकता है एक ये होगा. सपोज इसको हम नाम देते हैं मैक्रो स्टेट नंबर 1. राइट? अब हम कहेंगे कि इसकी thermodynamic probability क्या है. राइट? Suppose we represent the thermodynamic probability. You know, in our lectures in the past, sometimes we represent it by omega. Here in Salinger, he represents it by capital W. So the thermodynamic probability of this macro state, I represent it by a big W. And I will say omega W1. Macro state number 1, the thermodynamic probability of the macro state number 1. If you remember, we say it will be the product of the number of ways in which these particles can be accommodated in this level and multiplied by the number of ways in which the particles can be accommodated in this level multiplied by the number of ways in which particle can be accommodated in this level. Right? And if you remember, it was pi, we represented by pi, the product. It is, you remember, it is like the sigma sign, but sigma is for summation and pi is for product, or multiplication. So we say pi I, and we represented the thermodynamic probability of each level by I, omega I. Omega I. So that will be equal to, look, this is level 1. So the thermodynamic, the number of ways in which these particles can be put in this level 1 will be omega 1. Omega 1. And multiplied by the number of ways in which these two particles can be accommodated in this level number 2. Let that is represented by omega 2. और ये जो है, these are irrelevant. ये levels हमारे लिए irrelevant हैं. These are irrelevant. These are not of our use. इसमें particles ही नहीं है ना. So the next is what is that? Omega 5. Right? Now, look, we do it now by just looking at the system. By just looking at the system, and we can find the number of ways. Suppose, look at this level. The particles are indistinguishable. They cannot be separated one from the other. They are exactly alike. So, this particle is like this particle is like this. So if you shuffle them, if you bring this particle here and this particle there, that will not give you a new state. It will be the same thing because the particles are exactly the same. अगर आप इसको यहाँ पर ले आए, इसको यहाँ पर ले आए, does not make any difference. इसने कोई change introduce नहीं किया. Right? So there is only one way. There is only one way in which particles can be accommodated or placed in level number 1. Only one way. So omega 1 is 1. Omega 1 is 1. There is only one way that the particles can be accommodated in 3 states. Here in this situation, all the states are filled. All the states are filled. Okay. Now, omega 2. So here there are 2 particles. These are indistinguishable. So this is one way. The one way is this. This state is empty and these 2 are filled. So this is one way. Now I can switch the particle from here, this state to this state. This will be empty, then this will be full. So that will be another way. Now I can bring this particle here. That particle was already here. So these 2 states will be full or filled. These 2 states will be filled and this will be empty. So there are only 3 ways in which these 2 particles can be accommodated in level number 2. There are only 3 ways and no more than that. Right? Okay. Let us go to level number 5. Right? Now, the box at the extreme left is filled. These 2 are open. So this is one way of putting the particle in the boxes. Now, if I have another choice, I can bring this particle here and this box will get empty and this will get filled. So that will be another way, a new way of putting this particle in this level part. Again, I can bring this particle to this state, the extreme right. So these 2 states will be open then and this will be filled. So again, there are only 3 ways, 3 distinguishable ways, 3 ways which are different from each other. 3 ways which are different from each other. So this single particle can be accommodated in the 3 boxes in level number 5. So, हमारे पास omega 5 जो है, that will be also equal to 3. Beta 5 will also be equal to 3. And what will be the total? Will be 9. So the thermodynamic probability of this macro state number 1 is equal to 9. Okay, so this is the thermodynamic probability on macro state number 1. Right? There are total 9 microstates in this macro state. Right? Now we can do the same. We did this by observation. We did this by observation. We can use our formula too. by formula. Right? We want to do it now by formula. If you remember, it was the formula for the FERMI-DIRAC statistics was equal to omega I, the number of ways in which particles can be placed in different ways, in which particle can be placed in different boxes, right? That was equal to GI, right? Factorial divided by GI minus NI factorial and NI factorial. That was the formula for the FERMI-DIRAC statistics, right? So now let us apply it here. So omega 1 will be equal to omega 1. Omega 1 will be equal to G1 divided by G1 minus N1 factorial and to N1 factorial. That would be for level number 1, right? Okay, so what is G1? G1, and that is prefix G1 factorial. G1 factorial. I again forgot the factorial here. So G1 factorial. What is G1 here? Level number 1 में कितने states हैं? That is given to us in the example. कि तमाम state, तमाम level में states जो हैं वो 3 हैं. Degeneracy तमाम levels की 3 है. That is GI. So G1 will be equal to 3 factorial divided by G1 3 minus what is the number of particles in 1? What is the number of particles in level number 1? The number of particles in level number 1 is 3, right? So minus 3 factorial multiplied by N1 again. The number of particles in level number 1 factorial. Number of particles is equal to 3. So it will be 3 factorial. Right? And this will be equal to 3 factorial divided by 0 factorial and to 3 factorial. And this will be equal to 1. So omega 1 is equal to 1. Okay? We got this by inspection. Omega 1 was equal to 1. We got this by inspection, by observation. It was equal to 1. And from formula, it is equal to 1, 2. Right? Similarly, omega 2 will be equal to 3 factorial divided by 3 minus 2 whole factorial and to 2 factorial. Right? And that comes out to be 3. Look. That is 1 factorial. 1 factorial will give you 1. That is 3 factorial, and this is 2 factorial. So this is 3 multiplied by 2, and this is 2. So 2 will cancel out, and you will get 3. So level number 2 has got 3 ways, right? Again, in level number 5, omega 5 will be equal to 3 factorial and divided by 3 minus omega 5 देखिए इसमें level number 4 में level number 5 में there is only one particle in level number 5. In level number 5 there is only one particle. So 3 minus 1 factorial multiplied by number of particles factorial, which is 1. So 1 factorial. Again, this is like this thing. Will be 2 factorial multiplied by 1 factorial. And this will give you, see, So we can get this by formula 133. 133. We can get this by formula, or we are clever enough. We can also do it with our observation, or at least some can be done very immediately. For example, I can just talk about this. Oh, this has the thermodynamic the number of microstates, and this is only one because there is only one way so that these particles can be. Okay. Now, after detailed discussion of this, I would like to make a table. I would like to make a table to discuss all the macrostates. Okay. Now, let me write this in a table format. Let me write this whole situation that will be. We discussed the first situation at very detail. Now, let me write it in. These are the energy levels. Now, the macro state number one, right? It was, we put, there were three states, and therefore only three particles in the first label. That was one, and the energy 0, E, 2E, 3E, 4E, 5E, and so on. 6E. Now here, only three particles. Suppose this is one macro state, right? Suppose it is layer number 1. So there are three particles, and there were two particles in the second, right? And in the fifth level, there was only one particle. This was the first macro state. We just did it. We just did it. I am doing that again for comparison with the rest of the macro states. That is level number 1. That is 2, that is 3, 4, 5, 6, 7, etc. Right? Now, another situation. Right? Another situation could be like three particles here, one particle here, one particle here. There is a different macro state. Now, should I call it? There is macro state number 2. Macro state number 2. Right? So, three particles here, one particle here. So, one particle here means it has energy only E. So the other particle suppose comes here. So it will have energy E plus 2E. E plus 2E will be equal to 3E. So the energy of the system is now 3E. Our system has 6E energy. So the next particle should go there, which has 3E energy. The next particle should go here, which has 3 energy. And that is macro state number 2. So for macro state number 2, we apply the formula, suppose, and that will be equal to pi I omega I, right? And that will be like omega 1 multiplied by omega 2 multiplied by omega 3 multiplied by omega 4, right? Okay, omega 1 we know that omega 1 is equal to 1, right? Omega 1 is equal to 1. Omega 2, we did it in the last situation. Omega 2 will be equal to 3. We did it, right? We did it in the case of the macro state number 1. We did it, the last level. This one, we did it for this one. It was 3. It was 3. So this will be 3. Sorry, this will be 3. Now omega 3 will also be equal to, because this is like this. And we did it. So omega 2 is equal to 3. Omega 3 is equal to 3. And omega 4 is equal to 3. So W, the thermodynamic probability of macro state 2 will be equal to 1 multiplied by 3 multiplied by 3 multiplied by 3. You can apply the formula to it. We did this. This is exactly the same. One particle in 3 states, one particle in 3 states, one particle in 3 states, one particle in 3 states. So here, W2, the thermodynamic probability of the state number 2. W2 will be equal to, it is a 9 and 27. Right? So W2, the macro state, the thermodynamic probability of the second macro state is equal to 27. Thermodynamic probability of macro state number 2 is 27. Now, let us think about the third one. Right? Let us think about the third one. So, another situation could be like 3 particles here, 3 particles here. And the energy of the system is now in this macro state number 3. The energy of the system, how much? It is 0 at this level. We are just going to complete the energy as well. So if it is 3, then what should we do? That we should put all the particles, or we are allowed to put all the 3 particles in this level, which has energy 2E. This has energy 2E. So the energy of each particle will be 2E, and there are 3 particles. So the total energy of the system will become 0 plus 6E equal to 6E. So this is the allowed macro state according to the condition of our system. because the energy will be 6E. So that is the other macro state. What is the thermodynamic probability again? The thermodynamic probability of this state, W of 3 will be equal to pi I pi I omega I, and that is equal to omega 1 and omega 3. So look, what is the you can apply the formula too, but look, what is the thermodynamic probability of this? So not the thermodynamic probability, the number of maximum number of ways. We call the thermodynamic probability for a whole macro state. So that is the number of ways in which the particle can be placed in these three states is equal to 1, like this, like this. So that is equal to 1. Similarly, omega 3 particles in 3 states, again the maximum, the number of ways to put, number of distinguishable ways to put these 3 particles in 3 states will be equal to 1. Right? So this will be equal to 1. Omega 3, sorry, W3 will be equal to 1 now. Question number? The thermodynamics probability of this state is 9, if you remember. Of this state is 27. Of this situation, it is okay. Now another case. Macro state number 4, you can say. 2 particles here. Suppose there are only 2 particles. We have 4 particles, and the energy required should be 6E from 4 particles. Right? So suppose 2 particles are here. 2 particles are here. Suppose 3 particles are here. Let's do that later on. 3 particles are here. So 3E energy from here. And this is 3E. Now, how much should be the energy of the rest of the situation? 3E here. And, oh, sorry, I should put it in this. I'm not here, sorry, I'm sorry. 3 particles here. 2E. I was just confused with these 2. So I should better not, I should just erase. So 2 particles here, 3 particles here, and 1 particle. I'm totally confused. If we have 2 particles here, that will be how much energy? 2E. Right? The remaining is 4. So 2 particles should be in the second, the third level. So then the energy is 6E. 2 are 4E plus 2E, and that will be equal to root of 6E. So that is the next macro state number 4. Right? So the thermodynamic probability here of this state. So W4 is equal to omega 1 multiplied by omega 2 multiplied by omega 3. Okay, omega 1 equal to right, gi factorial to g1 factorial divided by g1 minus n1 factorial and n1 factorial. n1 factorial, right? g1 factorial is equal to 3 factorial. There are only 3 states, right? g1, right? The states are g, particles are 2. So 1 factorial. How many particles? n1 factorial is equal to 2. So 2 factorial. So that will be equal to how much? 3 factorial divided by 2 factorial, which is equal to 3. Since the remaining are also like this one, so their situation is the same. So omega 2 will also be equal to 3, and omega 3 will also be equal to 3. Right? So W4 will be equal to 3 multiplied by 3 multiplied by 3, which comes out to be 27. If I write the thermodynamic probability under each of the macro states, then the first one was this was 9. If you remember, the thermodynamic probability of this was 9, right? And this was 27. This was, we just said, 1, right? And this is 27 again. 27 again. Now, what is the situation we are left with? Omega 5. Now, we want to fulfill the condition of 6E and keeping in our mind the Pauli exclusion principle obeying particles, right? So, if we put two particles here. So we are left with four particles. We are left with four particles, right? So suppose we have one particle here. So there is one particle here, and the system energy is now equal to 1e. We three particles have gone, and we have the energy of the system equal to how much? 1e. So 6 minus 1 is equal to 5. 5e. हमारे पास एनर्जी, हमारे पास पार्टिकल 3 है, 5e एनर्जी है, right? So the situation if I put one particle over here, this is not the situation. मैं अपनी टेबल जो है वो मैंने अपनी पूरी नहीं लिखी है. Now I am solving this like you will be solving it. So there is 2 here, 1 here. It is like this situation, but now we have 5 E left and only 3 particles. So if I put 2 particles here, that would be 2e, and one of the particles here, one of the particles here. This will be not be the situation, right? 1e plus 2e equal to 3e plus a particle in energy level number 3, that will be equal to 6e. So that is another macro state. Let us find out what is the thermodynamic probability of this macro state. Right? They are, it is equal to omega 1 multiplied by.
Sir, excuse me, sir.
Yes.
सर ये 2e एनर्जी लेवल में तो 2 पार्टिकल है, तो फिर तो ये एनर्जी ज्यादा हो रही है.
ज्यादा हो रही है? Oh yes, thank you. करते हैं. अगर हम इसमें से 2 डालें और इसको 1 करें, इस तरह करते हैं. 2, right? 2e plus 2e. No. This is not the check. मैंने अपनी उसमें टेबल नहीं लिखी है, भूल गया हमें टेबल अपना उसमें अपने नोट्स में. तो इसलिए अभी हम इसको we have to figure it out.
सर
Yes.
सर ये 3 वाला जो है, अगर इसको पूरी में रख दे तो फिर ठीक हो जाता है.
अच्छा देखिए, इसको पूरी में रखें. तो जो इसको पूरी में रखेंगे तो we have one state like that before, right? इसको हम जो है वो पूरी में रखेंगे तो we have already this state.
सर इसमें तो 3 पार्टिकल्स है 0 में.
All right, इसमें here there are 3 particles and here we have 2 particles. So 2 particles this is having, that will be like 2e, right? Plus this one. So that will become 5e. You are right. So इसको हम आगे 3 कर लें 3e, right? 3 particles. So 3e, and that will be 1 3e. ये है हमारे पास कि नहीं है? Do we have this? Do we have this?
नो सर अभी ठीक
We do not have it probably. Look, 0, it will be like 0 plus 3e plus 3e. Right? So that will be 6e. Is it okay now?
यस सर अभी ठीक है
Condition तो पूरे हो गए हैं ना?
यस सर
And we also do not have it like here. यहाँ पर हमारे पास है भी नहीं इस तरह का कोई.
नो सर
Okay.
नो सर
So omega 1 multiplied by omega 2 multiplied by omega 4. Omega 4. Omega 1 is equal to 2 particles in one state. It is like the same situation. We did this in the first case. Right? This situation is this one. दूर क्यों जाए हम? ये तो यहाँ पर इसी का. This is the same thing as this one. So omega 1 is equal to 3 multiplied by. इसमें 3 1 जिस तरह हमने ये किया ये then always they were having the omega was equal to 1. There was only one way. Now here this one, right? We already did it like this. They all have 1. So this number of ways are equal to 3. आप formula भी apply कर सकते हैं. You can also apply the formula. So it is equal to 9. So W5 is equal to 9 again. This is हमारे पास कितने equation बन गए? This was the question number 4, and this was the question number 5. Am I right? Right?
Yes, sir. Yes, sir.
Thank you. Look. This is 27, and this is how much? 9. Right? And according to our calculation, we do not have another macro state which is different from these 5. So only these 5 macro states are possible in this situation, right? 1, 2, 3, 4, 5. These 5 macro states are possible, right? So this is the answer to the first question. The thermodynamic probability of find the thermodynamic probability of each macro state. Calculate or write down the thermodynamic probability of each macro state. The thermodynamic probability of state number 1 is 9. Number 2 is this. What is the most probable distribution? Right? Are the most probable macro state. The most probable. Which one is the most probable? Do you remember it? You know, most probable कौन सी होगी? आपको याद है ये हमारे पिछले discussion से? Do you remember something? It was like that macro state will be the most probable, which has the maximum number of microstates. इसमें microstates now has the that is macrostate में. Here, this is 27. This macrostate has microstate 27. This macrostate has 1. This macrostate has 27, which is 9. So सबसे ज़्यादा जो है वो इनमें. हमारे हिसाब से macrostate number 2 or 4. W2 and W4 are the most probable. Macrostates, the most probable distribution, right? And the least probable is with the smallest number of microstate, which is this one. So the least probable is number W3 with 1 microstate. With only 1 microstate. So that is the least probable. These two are the most probable distribution. Okay, so what is the total number of? देखिए ये आपकी किताब में अगर ये आगे पीछे हैं तो इससे आप कंफ्यूज ना हो. You know, the most important thing is how much is the number of microstate. Which macrostate has the most number of microstates? That would be the most probable, right? Okay. What is the total number of? The total number of microstates. Total number of microstates. It has been written as macrostate in your book, but that is wrong. That is some typing error. So it is microstate. The total number of microstate. Let's go. I would write it like W is equal to sigma and to Wi. Sigma Wi. Right? That will be equal to, right, 9 plus 27 plus 1 plus 27 plus 9. And that is equal to 73. Total number of microstates is equal to 73 इस सिस्टम में हमारे पास जो सिस्टम है the total number of microstates in this situation is equal to 73. This is the total number of microstates possible whatever is the distribution of the particles in any macrostate. Okay, now we want to go to find the average number of particles in each level. Right? Average number of particles in each level. On the average इस level में कितने हैं? देखिए, level 1 में this is level 1. That is level 1. So most of the time this level is filled. Only in this situation and in this situation it is partially filled. In most of the situations, in all the situations, this is whatever the situation may be, whatever the macro state may be, this level number 1 is full, except two situations in which there is one chair empty, one particle missing. So let us find what is the average number of particles in this level. इस लेवल में आमतौर पर हमारे पास जो भी डिस्ट्रीब्यूशन हो, what is the what is the total number of the average number of particles, and this is called the average occupation number. So I don't know what was the average occupation number. The average occupation number of each level. हर एक लेवल की एवरेज ऑक्यूपेशन नंबर क्या है? हर एक लेवल की एवरेज ऑक्यूपेशन नंबर क्या है? We have done a formula for that, the average occupation number. And this is kind of the weighted average that we have done in your metric. Exactly like that. So the average occupation number in any level J or I, आप इसको I कहना चाहते हैं या J? आपकी किताब में J लिखा हुआ है, therefore I would write J. I wrote it I here, but I and J the same thing. That is just an index. So you should take the notice that I and J, I is the same thing. Sometimes I write J, sometimes I write I, but your book writes J. So in level number J, right, this is J's node. In level number J, the average number of particles will be equal to the sum of the particles in each level. Sum of the particles in each level, right? In each macro state, N, J, right? In K, right? And WK. divided by the total number of microstates. Your book writes this is omega. The Sears and Salinger book writes this symbol is the omega, capital omega. But I write it as capital W, not to confuse with our previous lecture. That is why I want to be like what we did in the past, since we are following different books and different situations. So there is summation over all the macro state. Summation over all the macro. इस macro state में आपके पास इस लेवल पर आप इस लेवल की बात करें, सपोज आप लेवल 1 की बात करें, तो इस लेवल पे आपके पास कितने हैं इस मैक्रो स्टेट में आप इन तब सब कुछ सम करें और डिवाइडेड बाय द टोटल नंबर ऑफ माइक्रो स्टेट्स ऑफ द सिस्टम. That is just like a simple average that you usually do. That is the formula. So I want to find, suppose, the average number of particles in level number 1. So it would be like this: level number 1, N1, macrostate number 1, right? Should I write is like 1, N1, and W1 plus so on, right? It will be like N1, and this was 5, N1, 5, and W, 5, right? Divided by capital W. So that will be N1, 1. Level number 1 में कितने हैं? 9. Total number of microstates is equal to 9, right? Total number of microstates is equal to 9. Level number 1 में. और number of particles इसमें कितने हैं? 3 हैं. और W1 हमारे पास क्या है? 9. Plus number of particles in this 3 multiplied by the number of microstate in this macrostate 27 plus the number of particles in this, right? That is 3 multiplied by the microstates in this macrostate 1 plus number of particles in this 2. Thermodynamic probability of this 27 plus number of particles here 2, and thermodynamic probability 9 divided by, if you remember, this was 73. That will be equal to, right, 1 over 73, and that is 27 plus 81 or something, and plus so on. It comes out to be 183 divided by 73. This is equal to 2.51. So the average number of particles in level number 1 This is called the average occupation number. The average number of particles in level is equal to 2.51, and it is true. It looks like true. You know, at the most, the occupation is 3. There are 3 particles at the most. Our कम से कम इसमें 2 है. So the average number 2 और 3 के दरमियान. The average occupation number of this level, level number 1, is between 2 and 3. And it makes sense. Look, when you look at this, या तो ये fully occupied है, or there are 2 particles. So the average number of particles in level number 1 is equal to 2.51. Similarly, N2 is procedure where now you N2 is equal to 1.73. Just follow the same situation. And 3 is equal to 1.15. And 4 is equal to 0.494, and 5 is equal to 0.123. Equation 6, 7, 8, 9, and 10, they give you the average occupation number of each level. The average occupation number of this level is 2.5, of the second is 1.73, of the third is 1.15, of the fourth is, so देखें जिस तरह जो है वो हॉस्टल में लोग ग्राउंड फ्लोर पे रहना पसंद करते हैं, फिर जो है इससे ज्यादा, फिर इससे ज्यादा, इस तरह ये पार्टिकल्स भी इस तरह कर रहे हैं. पहले ग्राउंड लेवल पे कितने हैं? सबसे ज्यादा पार्टिकल्स हैं. ग्राउंड लेवल पर सबसे ज्यादा लोग हैं. लोग किस कहते हैं? हमें जी पहले मंजिल पे जगह मिलनी चाहिए. So this is more than this one. The second level is more than the third. The third is more than the fifth. जितना आप ऊपर जाते हैं, as you go up, the occupation number is decreasing. There are less and less number of particles in the level. So this is the average occupation number of each level. Level 1, level 2, level 3, level 4, level 5. And another interesting situation. What is the sum of all the occupation number? आप देखें अपने लिए करें. What is the total occupation number? देखें आप इसको काउंट करें and देखें कि क्या आता है. The total occupation number. Okay. This was a technical kind of problem, and then we tried to solve it in detail. And if you have any questions, you can send me email, you can call me anytime, we can discuss it, right? And sometimes there is a question like this in examination. Maybe आपके papers में कभी कभार आया हो. So hopefully next time we will be doing the free electron gas. We will be applying our FERMI DIRAC statistics to particles in real life. that is electrons in conductors. We will be applying the statistics, the Fermi-Dirac statistics, to electrons in conductors. This is suppose a conducting wire. So there we say there are electrons. These electrons are not bound to the outer electrons of each atom. They are supposed to be free. They are not bound to each particular nucleus very tightly. जो दूर के इलेक्ट्रॉन्स होते हैं वो relatively free होते हैं. So we will be using our Fermi-Dirac statistics to analyze the situation of electrons in a conductor, and we will be finding different parameters and different properties of electrons inside a conductor with the help of Fermi-Dirac statistics. That would be application of the Fermi-Dirac statistics to discuss with the help of Fermi-Dirac statistics the situation of electron gas. We consider the electrons as a gas. Then we suppose inside the conductor the electrons are free. The electrons are free. They are not bound to a particular nucleus, particularly the outer electrons. जो दूर के electrons होते हैं, they are not bound to a particular nucleus, and they are inside the conductor. They are kind of free. There is no force on them. The only force these electrons feel is when they come to the surface. When they come to the surface, there is a force. Right? They are attracted inward. So there is only force. But inside the conductors, they can be considered as free electrons, like the molecules of a gas. So we will be doing this hopefully in our next lecture. But I am not happy with the situation that we have here. We have only few students here. Maybe I will then give you some